Hello, class. So I know I said we were going to do a video, but I'm doing a recording instead. So today I just want to go over your midterm. And you should have all received your midterm. I posted it, and it looks like everybody viewed their midterm. If you have any questions, I'll be happy to go over it when I get back Monday. So save your question, or well, yeah, because I won't be able to hear your questions. So I guess save your questions. But let's go through the test right now. And like I said, we'll go. If you have any questions Monday, we will go through them. Okay, so the first one, the influence line shown in Figure 1 corresponds to the beam below it. What feature is it for? Okay, so for this one, what you should be able to do is put your unit load. So basically you're going to be putting your unit load on here and see what feature is that correspond to. So you know that for reactions, your unit load, if your unit load is placed on the reaction, then the influence line at that point is equal to 1. So if we were to put our unit load at A, we should have a reaction of A, a reaction of 1 at A. And so in this case, we don't. This influence line doesn't, so we can cross this one off. If we put our, let's just do the reactions first. If we put our unit load at C, we would have a reaction of 1, and we do not. So we can cross that off. If we put a unit load for the shear at B, now the shear at B, we know if you have an influence line and you put your load at that location, there'll be a jump at that location for your influence line. And so in this case, there's not. So if we come over here and we put our unit load at 8, what is the moment at 8? At A, I'm sorry. So the moment at A, the influence line, if we do some of the moments about A, equal to 0. And what we do with this, because we have a pin, a hinge right here, we can just put this right here. And we know that when we separate this out, this is just going to be equal and opposite, right? And since there's no moment in the hinge, since it's a hinge, there's no moment there. So this is 8 feet. We put our unit load here. We take the sum of the moments about A. Let's just make it positive. It doesn't really matter. So that we have MA going in that direction minus 1 kip times 8 equals 0. Therefore, MA, when X is equal to 8 feet, MA is equal to 8 kip feet. So this influence line corresponds to the moment at A. So that's our solution for this one. Okay, the next one. What is the correct number of indeterminacies for the structure in Figure 2? We have kinematics. So kinematics, we have 3 equations of kinematics. I'm sorry, of statics, 3 equations of statics. We have 2 here, 2 reactions here. So we have AX, AY, and then we've got, 3 reactions here because this is fixed. So we have 1, 2, 3, 4, 5 degrees, or sorry, not 5 degrees, 5 unknowns. And 3 equations of statics with 3 equations. So 2 degrees static indeterminacy. Okay, so we've got 2 degrees of static indeterminacy. So let's verify for kinematic. So for kinematic, what do we have? We know we have rotation here. We're going to have the beam coming out here. That's going to be our deflected shape. So we know we're going to have one displacement here, one displacement here. That displacement is going to be the same. And now as I go through this, I realize we've got a rotation here, theta B, and we've got a rotation here, theta C. This is rotation A. So this is actually 4. So if you selected A or B, let me know. I marked off for this one. It should be 2 degrees static, 4 degrees kinematic. So if you got that far, you know that you have side sway in here. So with side sway, your answer for this one is yes, you will have side sway. Structure will sway, side sway. And the reason of this is because our boundary conditions are not symmetric. Whoops. So you've got rotation capacity here and then fixity here. So you won't have any rotation. So this isn't going to want to go into double curvature. It's going to just bend. And then this one is going to just rotate. Okay? So again, if you put A or B, I think I just corrected for B, gave you points. But if you put A and let me know, I could go back and look at everything, but it would be a lot easier if you just let me know. All right, so the next one is use virtual work to compute the vertical displacement of joint C in the truss shown in figure 3. Okay, I gave you different areas for members A, B, and A, B, B, C, and C, D. And these members, the remaining members, were 0.25 square inches. Okay, so what you needed to do is solve for this using virtual work to compute the vertical displacement at joint C. So what you needed to do, this is a statically determinate truss. Statically determinate. So you should go through and you get your P system. So your P system is this one. And then you're going to solve for your Q system. We'll get blue by putting a point load in the direction of the displacement that you want. Okay? And so I put mine going down in this direction because I'm going to say that I'm going to expect this under this load condition to deflect down at point C, because there isn't really anything that's going to make it deflect up. And so the only reason I did that is just because then I don't have to mess with any signs. But if my sign comes up negative, then that means I assumed the wrong direction. Okay, let's make this guy smaller. Okay, so for your P system, solve for the reactions. Some of the moments about A was the most simple for me. So my dy was equal to 3.86 going up. Let's use a different color. So dy, so I got a positive value, so I assume that in the correct direction. I solved for my ay by just doing some of the forces in the y direction with positive going up. So my ay was equal to 11.14 going up, because that's the direction I ended up with a positive value, and so I assume that direction to be up. In the x direction, my ax is just equal to the 10 kip load here, and it's going to be equal and opposite to that direction. So then solve for reaction. So then the next step is going to be do method of joints. To solve for member forces. Okay, so the first thing, I like to choose D, because it's just got one vertical component, and then that means that this guy is going to come in this direction, okay, to balance it out. I've assumed this going this way, so that means that this is going to be my only contribution to the vertical component, so that I'm going to have a component of that going in this direction, and a component going in that direction. So then if this one is going to be going in that direction, there's no reaction in this direction. That means that member DE is going to be acting in this direction. Okay? So DE is going in this direction. The component from CD is going in this direction. So those two are going to balance out. And so if you recognize that this is a 6-8, that means this is a 4-3-5 triangle. So that means that this member is 10 long. Okay, so that member's 10, except you need to look over here. This is 5, so this is a 4-5, it's not a 3-4-5 triangle. So you should be able to go through and see that this member is equal to 9. I think I may have it down here. No, I don't. It was equal to 9 something. Let me see, is it on here? Ah, the beauty of recording, I can pause and come back. 9.4, whoops. I got 434 for this guy. Okay, so that gives you all your member lengths. This one is 10 again. This is going to be 9.434. So you should be able to solve for all of these very easily at this point. So using method of joints to solve for these members, I started with, I start with dy. My vertical reaction is the dy value that we solved for up here, 3.86. Oh my goodness. 3.86. And then, since this is a 3-4-5 triangle, I can just take this DC value, the component, this is my DC right here, The horizontal component is going to be 3/5 of that. The vertical component is 4/5. Vertical component is going to be equal to my vertical reaction. Therefore, I can solve for DC. DC is equal to 4.825. And this one is pointing toward the joint. So that means that member is in compression. Okay, so then the DE, the horizontal component, is equal to 3/5 of the DC member. So we've set this up to be, we know what direction this one is going, this component. So this component DE, the member D, force DE needs to go in the opposite direction. It comes up to be 2.895 times, and that's a tension force. Okay, now going through and solving, I'm going to take joint AE and solve for that. At joint A. At joint A, I've got the same sort of condition. I've got a 10 kip load in here, and we don't really know which way this one is going. So I'm going to just say it's going this way. This is going to be this angle coming back up here, if you want. This angle up here to make it easier on yourself. If you don't want to do the 3, 4, 5, you could also, to check it, this is a 10, 6, 8 for the vertical, so that this theta, tangent of theta, is equal to opposite over adjacent, 8/6, so that theta is equal to 53.13. So coming down here, this angle is the same, 53.3 degrees. You can see there, 313.13, sorry, 53.13 degrees. My AB member is this, is AB. AB is equal to 13.9, because I'm taking this value of 11.14. 11.14, I'm going to convert into this component so that my AB is equal to 13.925, because I'm balancing this force now. So with this component, I want to take the horizontal component of it, this member, AB, the X component, is equal to 8.355. So here, this is AE, summing up in the X direction, this equals 0. Make this go positive, so that I have this AX component. This AX is the 10 kips. This is your A sub X, minus, because I have it going in this direction, minus ABX, the horizontal component of AB. This gives me 1.645 for member AE. And this is in compression. So both of these are in compression. Okay, let's see what's next. So the next one I did was joint C, just for fun, to jump over there. So joint C, here I've shown the angles, because we've got this triangle here. This triangle is 53.13, okay? This triangle, this one is only 5, which is what we're showing here. This one is 6 feet, but this is still 8, such that this angle now, this theta 2 angle, is equal to theta 2 is equal to tangent of opposite over adjacent. So tangent of theta 2 is equal to opposite over adjacent, 5 over 8, such that my theta 2 is equal to 32 degrees. This is my theta 1. And theta 1, if this is equal to 90, theta 1 is equal to 90 minus 53.13, so that theta 1 is equal to 36.87. So now I've got my two angles. I can just come in here to joint C. We solve for this member in the last problem, which was equal to what was that equal to? CD was equal to 4.85. Yes, right here. 4.85. So CD, this was equal to 4.825. But we also know that that vertical component of CD was equal to this value. Okay, so if that vertical component of CD is equal to that value, then the vertical component of CE has to be equal to that value. To get the vertical component of CE, it's the cosine, it's CE times the cosine theta 2. That equals 3.86 kips. So dividing by theta 2, cosine theta 2, our CE is equal to 4.55 kips. And it's pulling away, so that member is in tension. Okay, so then to solve for CB, all we need to do is do the sum of the forces in the x direction. CB, I'm saying, so since we know that this one has to go, this one is going up, it's in compression, we know that it's only balanced by a vertical component from here, so this guy has to be going down. So these horizontal components are both going to be going to the left. So that means CB has to go to the right. So if we say positive to the right, that means CB is your only positive member minus the horizontal component of CD and CE. So that gives me my CB member is equal to 5.307, and that's in compression. So let's take this all the way over to joint B, and that's really messy. Okay, so let's take this over to joint B. We just solved for that. Whoops. So that's this one. We have this going in this direction. We have this 10 kips that's applied going in that direction. We have the AB that we solved for previously, and we know that that was in compression, and so it's going in this direction. So if this is going in this direction to go, the vertical component of it is going to be going in this direction. And so that means the horizontal component is going in this direction. But to balance this vertical component, the only thing that can balance that is BE's vertical component. So that means BE has to be going in this direction such that its vertical component goes in that direction. Okay, and so if you assume these are the wrong, it doesn't matter, you'll just get a negative sign. So just keep track of it. But if you can figure out where it's going to go first, then you save yourself the trouble of switching signs. Okay, but if not, don't worry about it. Okay, so first thing we'll do is sum of the forces in the y direction. We only have components, vertical components from AB and BE, and so we have these angles are the same. Theta 2 is on the inside now, and theta 1 is on the outside, so that corresponds with that one, such that your BE is equal to 13.13. It's pulling away, so it's in tension. Okay, so what we had here was we've solved for all of the members. So if you want to check this, what you have, you still have joint E that you haven't used it all yet. So you can use joint E to check. And so when you do your equilibrium at joint E, it should all match up. Okay, so you're not solving for anything. You just use joint E to check. So coming down here to joint E, we've got the 15 kips going down. We've got AE going to the left, DE going to the right, and then we've got BE and CE, which we solved for. BE was equal to 13.13. CE was equal to 4.55. And now the angle here, we've got, looking back up here, we just need to solve for what this angle is. This is theta 3 down at the bottom, right? That's this guy right here. So coming back down here, let's look at it. Theta 3 is equal to, we have theta 2 here. This is a 90. So 90 minus theta 2 equals theta 3. So that theta 3 is equal to 58. The vertical components of these were both in tension. They're both pulling away, so they're both in tension. They're both, the vertical components are both going to be going up. Therefore, the sum of the vertical components are going to be equal to 15. If they do, then you balanced everything correctly. So you've done your model correctly, or done your method of joints correctly. And so you should always be doing a check like that. Usually trusses will come out so that you have an extra node, an extra joint that you didn't need to solve for, and you can use that to check your work. All right, so this is our P system now. So P system complete. Now you need to analyze your Q system. So same thing, find your reactions. I've applied a 1 kip load going down at C because we want to find the vertical deflection at C. So we'll put a load in the direction that we want. Solve for our reactions. We don't have any external load in the X direction at A, or we don't have any horizontal load in. So therefore, A sub X is equal to 0. We take some of the moments about A. This gives us dy times 22 minus 1 kip times 16 feet. Therefore, my dy is equal to 0.727 kips going up. And then I just do my sum of my forces. I've got ay going up minus 1 kip plus 0.727. This gives us ay is equal to, that's a 0.273. Okay, so now I just do method of joints, go through. I won't go through all of this, but I will post this for you all and you can see it. My CD value, just using the same principles. The geometry hasn't changed, so none of our angles change. All of our cosine directions are all the same. So you should be able to follow through where you get CD is equal to 0.909, DE was equal to 0.545. At joint A, AE is equal to 0.25 in tension, AB was equal to 0.34 in compression. And now with these, you're going to assign, well, we'll get to that next. And then joint C, you can use to solve for member CE and member CB, okay? Where you end up with CE is equal to 0.32 in compression and CB is equal to 0.375 in compression. Okay, so now in this, what you need to understand and make sure that you recognize, it doesn't matter what you use for sign conventions, you just need to be consistent. Okay, so with this, we're going to say compression is negative. Okay, so you've got your orientations and everything. So when you go and put it in your table, oh, and you have to go through and do joint B to solve for BE. So putting it in your table, members in tension. Whoa, sorry. I'm going to use my sign convention here, because you're figuring out what direction you're going in. Tension, I'm going to use positive. Compression, I'm going to use negative. Okay. I set up my table with all my members, and then I get all my FP forces, my forces from the P system. If it's compression, I put a negative sign in front. I do the same thing with my forces from my Q system. If it's compression, I put a negative in front. I line up my L values and put them in inches to make it easy on myself. And then I put in my area value and put those in inches. But I don't have to convert anything. Then I do my FP forces times my FQ forces times my length divided by my areas. I save dividing by E till the very end because it's the same. There's no point in trying to type that in. How many times would we have to do it? An extra 7 times. So I add these all up and then divide them by E, and that gives me 0.276 kip inches. This is equal to 1 kip time a displacement in the vertical direction at C. Divide it by 1 kip to end up with displacement at the vertical direction at C is equal to 0.276. My sign came up to be positive, so the direction that I assumed was correct, so that my direction is displacement going down. Okay, so a lot of people had 0.32, I think, and I think that was just round off, so everybody got credit for that. And I think I graded pretty fair on and easy on this one. If you just made some math errors, I just took a point or two off, depending on how excessive the extent of your math errors were, if there were a lot of math errors. And again, so on the final, what I would expect you to be doing is coming back, and if I did put a point on here, do a check. That's going to eliminate a lot of your math errors. So go back and check with your extra joint and see that your forces are adding up, and that will eliminate your math errors. And then the round off, I didn't take any points off for that. Okay, so the next problem, and this one was worth 25 if I recall right. The next problem, I wanted you to analyze the beam in figure 4 using flexibility method and use R sub C as your redundant. So that means I want you to use R sub C, I'm repeating myself, as your redundant. So that means you're going to remove it. You're going to solve your system with this removed, and then you're going to solve the system with this applied. Okay? So with RC removed, my deflected shape's going to look like this. And then I'm going to say the deflection that occurs, oh, let me put the force in there because there's actually this point load here. And that is your load of 36 kips. And that's going to give me a deflection. Okay? And so note, this part of the beam is just going along for the ride. So it's straight. Okay? So your curve's coming like this, and then it's going straight from there. Okay? Just a tangent at that point. So the thing that you needed to recognize is that you needed to solve for the deflection at C. Okay? So this is not the same thing as solving for the deflection if the point load is here over the full length. Okay? This would be 15 feet. Okay? So your deflection here would have curvature all the way through the section. So you could have done one of two things. So you didn't know, you couldn't just use the cantilever equation for this deflection. This deflection, let's call this cantilevered, is not equal to the deflection C naught over here with the point load moved in. So as you can imagine, it should be less, right? Because at this point, it's just going, it's just tangent. Whereas this one, it has its own curvature within it, okay? So this value is not equal to this value, so you couldn't just go and use the equation from the back of the book for a cantilever section. You can, however, use that for your next problem where you've got the cantilever with the load going up, but it's not the same as for this one when the load is at this point. Okay, so that was the thing that you needed to recognize on that. And so since you guys are pros at moment area method now, you should be able to use moment area method to find the deflection. Some people recognized the difference, and I think that they use superposition to find the deflection at this when the point load is right here. Okay, so to get the deflection here, you can use moment area method. And so this deflection is equal to your line drawn from a tangent at C with respect to A. So this is going to be the moment about C with respect to A. So what that's going to be is the moment of the moment diagram when you've got, so this is your point load right here. That's going to give you a moment of 36 kips times 9 feet. This comes out to 324 kip feet. My moment looks like this. And then taking the moment of the M over EI diagram, if I put this over EI, MA prime over EI, I'm going to have 1/2. So I take the area of this. This is just your moment area. 1/2 base times height. So that's this part. This is the area of your M over EI. And this is your moment arm from point C, 12 feet. So you have 17,496 over EI for your deflection. So compatibility, we're using this, requires a reaction that will produce the deflection in the opposite direction as that produced here. And so here is where you can use, because we're plugging RC back in, RC, which is going to be what our reaction is to bring this guy right back down. RC, the deflection that is caused by that is equal to your PL cubed over 3EI, and that's from table A3. All right, so in the final position or the final configuration, delta C is equal to 0. Okay, and so that means that the change in C naught when you remove the reaction needs to be equal and opposite to the change in C when you apply a reaction of C, or reaction at C. So you solve for that based on these deflections such that your reaction at C then is equal to 15.52 kips. Okay? And so now once you have that, you can solve for your MA. Your MA due to the reaction is equal to minus 232.8 kip feet. Okay, so once you have that, you can come back in and use equilibrium and statics. You solve for your vertical reactions. You've got 36 kips going down. You've got the reaction at C going up. And the reaction at A, this is all needs to sum up to be equal to 0, so you can solve for the reaction at A. The vertical reaction to be AY is equal to 20.45. Okay? And using superposition, you can find that your moment, you've got your moment from, we did this up here, you've got your moment from just the point load, 324. And then you've got your moment from the reaction, minus 232, such that your final moment then is going to be 324 is your MA prime plus your M double prime A. You've got 324 minus 232. This gives you your final moment of 91.2 kip feet. All right, so you should be able to draw your shear diagram now. You've got your reaction at A and your reaction at C. This ends up being negative. This difference needs to be, as you should know, this difference is the 36 kips. And then your moment diagram looks like this, where you've got this point load here. It's coming up to where that load goes in and then goes down to where you've got 0. And this ends up being 92.9. Okay? And now the last problem was to analyze the beam in figure 5 by slope deflection method. Draw the deflected shape. This is what your deflected shape should look like. You should recognize that since this is symmetric, and you see how you've got the deflected shape here, your angle here and here is going to be equal to 0. So your theta C is equal to 0. So your boundary conditions and your loads are symmetric about C. So that makes it nice and easy, because what you can do then is just do fixed in moments. Okay, so because this is slope is equal to 0 here, we can draw this deflected shape. That's a little sloppy, but you've got the slope is equal to 0 here, slope is equal to 0 here. This is the same thing as a fixed section. Okay, so let's just analyze the section from A, B, and C. So our fixed in moments come to your table A4, section E. We can figure out what our moment at A is minus 104.17 kilonewtons per meter, or kilonewton meters, sorry. And then your fixed in moment CA is equal to 11 WL squared over 192. That comes out to be 229.17 kilonewton meters. Your slope deflection then, use your slope deflection equation. It's near for MAC, moment at the near end and the far end with respect to the far end is equal to 2 EI over L times the quantity of 2 theta A plus theta C minus 3 psi AC plus the fixed in moment AC. Okay, so this is easy because this all goes to 0, such that now our moment AC is just equal to our fixed in moment AC, and our moment CA is equal to our fixed in moment CA. All right, so once you recognize all that, let's blow up the structure and apply equilibrium. So if we blow it up and apply equilibrium, we can solve for CY here. Okay, let's do the sum of the moments about A. Make this guy positive in this direction. Solve for CY. We've got our moments and our moments and our load. This comes out to be CY, and this is just due to the left side, so member ABC, correct? So from member ABC, we solve for CY. Then we can use that to solve for AY by just doing the sum of the forces in the Y direction. That gives us AY. And now we just take it and apply it in statics. So up here we've got, or AY we solve for 37.5. So let's go back and look at our drawing. Make it 37.5 kips going up. We've got 162.5 on this side from ABC, and then 162.5 from CDE. So that means that we've got 2 times that. And then on this side we've got 37.45 going up. Okay? So we can draw our shear diagram then. 37.5 going up. We've got no load on here until we get to here, and then we have a constant load coming down. We've got a reaction here, so when we've got a vertical reaction, it goes straight up, and then we've got the constant load going down until we get to the end of that load. We cross over, there's no load, and this equals 37.5, which is our reaction going up. Our moment, because recall, this is fixed here and here. So your moment, you guys should be looking at this and saying, okay, I'm going to have a moment here. I'm going to have a moment here. I'm going to have a moment here. And then this is going to be So I've got a moment here at this face, and I've got a moment at this face. I'm going to have a moment at this face. And then the load, this is going to be going straight because there's no load on it. And then as I've got this load applied, there's going to be curving on here until it comes down and then comes back up. And then it's straight till I go back down here. So you should know that you're going to have a moment down here and you've got a moment down here, because at the very least this is fixed. So you know you've got moment here, and then you know that you've got, because this is continuous and because your rotation is 0 here, in order to keep that from having a point, you have to have moment in there as well. Okay, so draw your moment diagram, and then also you can be looking at your moment diagram. You know you start with a moment, okay, and you solve for that moment already, so you've got that moment. You solve for that moment and take it straight here, going in this direction, because this, remember, this is the flat. So then this is going to be 1 degree up, and then this is sloped. So then this needs to be curved to a point down to here, and then same thing up here, and then this is flat, so this is just a 1 degree going this way. And that should be your moment diagram for that. So a lot of people had it kind of offset. I think I just took a point or two off for that. I don't recall. But you should have been able to, you should have at the very least recognized that there's a moment here, that this is not 0 at this location. Okay? And then for this last one, if you made any attempt, you got full credit for it. And that's all we'll say about that. So I don't have any homework for this weekend. Enjoy your weekend, and I will see you on Monday. Have a great weekend.